Alright, I would like to take a little step forward, and we can talk a little bit about stability, and we can talk about stability looking at another problem, actually, another example. So we have to consider, we have to consider a system that looks like this. So here we have a rod that is connected to the ground through a hinge, and then we have a certain mass on top of this rod. This is also connected to two springs, and the two springs are connected to each other, the two springs are connected to the rod in the middle of the rod. So this would be the entire length. We can call this L, and then this quantity here is L over 2, so it's half of the length of the rod. So what we want to do, we want to derive the equation of motion. Of course, here we have the mass m. So I want to give you a few minutes to think about this problem. In this case, we can use the force method. We can look at all the forces involved in this, in this system, and then again we can try to derive the equation of motion. So please think about this for a couple of minutes. Yeah, the springs are the same, and they both have K as an elastic constant. Alright, we are all back, so you had a few minutes to think about how to solve this problem. Any idea, any suggestion on what we should do to solve the problem? Yes. Yes, I can describe a little bit more in detail the problem, the system. So here we have a rod, like a vertical rod, that is attached to a mass on top, mass m, okay? On the bottom, so to the ground, it is connected to, again, to the ground through a hinge, basically. So what happened in this case is that here we have this, this rod, and the motion of this rod with respect to this point would look like this. Okay, so this configuration actually has a name because this is called inverted pendulum. So if you have like a regular pendulum, it would, okay, let me do like this, it would do like this. But since it is an inverted pendulum, it is again connected on the bottom, and the oscillation occurs like this. Okay, now here we also have the contribution of the springs, which means that this is something that for sure we have to include when we look at the equation of motion, because they are going to apply some force on the rod, which means that they are going to influence the motion, which means that from a mathematical point of view somehow they will show up in the equation of motion. Make sense? Now, the other parameter that we need to look at is that the length of the rod is L, and also the springs are connected to the rod at L over 2. So this distance is L over 2, and the whole length is L. Makes sense? So now that we have a little bit more details, how should we approach this problem? First, we should determine what type of motion is. We should determine again what kind of system, and we already said that we will use the force method. We should also determine how these two springs are connected to the rod. So, any suggestion? Any idea? Yeah. We are using the force method or moment method. Let's say the Newton. Let's say the Newton method. So forces or moments. Oh, okay. I think you can do that as well. I'm using this one also, since we just saw a couple of problems with the energy method. I would like to also use this problem to do a little bit of practice with the force method. But would be a very good, very good practice to solve with the energy method as well after we look at the force method or the Newton method. So, suggestions. Yes, I agree. So in this case, what we are observing is the rotation of this rod with respect to this point. So if we want to use the Newton method, the best way to approach this is to look at the summation of moments about this point here. Now the next step is to look at the moments that are applied on this. So let's do a little bit of schematic. Here we have the ground. This vertical will be the equilibrium position. So let's assume we are in a position that is different from the equilibrium. Of course, I'm going to exaggerate the deflection, but we always need to assume that we are in the under the assumption of small deflection. So I'm going to create again a big angle, but we know that in reality the angle is very big. It means very small. Sorry. So here we have a certain angle theta, and here we have the mass, and then around the middle, at the middle actually of the rod, the springs are attached. So if this is the case, what are the forces involved, and how do we represent the forces involved in this system? Very good. We can use the K equivalent because we have two springs. How are these springs connected to the rod? Are they in parallel or in series? They are in parallel because again, this is a big displacement, but if we consider like a small deflection, small displacement, the two springs, every time there is again displacement of the vertical rod, they are subjected to the same deflection, which is from one side would be a stretching, and from the other side would be a compression, but the amount is the same. So since they are subjected to the same displacement, it means that the springs are in parallel. Okay. The springs are in parallel, they are subjected to the same, so we can, if we assume like this displacement, so towards right, this means that the force of both springs is in this direction, right? Because if the rod is moving in this direction, this spring is compressed, which means that it's pushing, in this direction. this spring is stretched, it means that it's pulling back our rod. So both forces act in this direction from the springs. So we can call this F from the springs. Anything else? We need to work on that, and for sure we have to include the contribution of the gravitational force. So the gravitational force is applied directly on the mass, and it is a vertical, so we can include the contribution of the gravitational force like this, right? So we have, this is m times g. So we are working on the forces. Now that we move to the moments, because again we have to do the equilibrium, or the rotational equilibrium, which means that we look at the summation of the moments with respect to point O would be equal to the moment of inertia multiplied by the rotational acceleration, right? In this case we can include our coordinate system. So if we have our x towards right, our y going upward, our positive moments are in this direction. So now we can consider all the contributions of the forces of the springs and the force of gravity, right? So let's start with the springs. So basically we have to calculate the moment of this force with respect to this point here, right? We multiply by 2 because again we have two springs. So we have 2 times k, which is the elastic constant of the spring, and then basically we have to look at this distance here, or this distance here. This distance is nothing but L over 2 multiplied by the sine of theta. This is the force of the spring, so it means that again 2k L2 sine theta. If theta is small, we can simplify, so we can replace sine theta with theta. We can simplify 2 and 2, so we have k L theta. This is the F spring. So now then we can finally write all the contribution of the forces for the spring and the gravitational in our equilibrium equation. So what we have is so we have KL so this is the force of the spring, and then L over 2 cosine theta is basically this distance here. Because again we have to calculate the moment of this force with respect to this point, which means this force times this distance here. And this is a positive moment because the moment of this force with respect to this point is counterclockwise. Then we look at the contribution of the gravity. So we have, in this case, the contribution is a negative contribution, so minus mg, and then we have to multiply by this distance here, which is L times sine of the angle theta. So this is summation of moments equal to this quantity here, which is m L square. theta double dot, and actually we have to put a negative sign in front, because if we have a rotation in this if we assume a rotation in the clockwise direction, it is a negative with respect to our coordinate system. This one, yeah. So this term is so the whole thing is the product between the force of the spring and the distance between the force of the spring and point O, like the pivotal point. So basically we are looking at this distance here. This is L over 2, so the projection of this here would be L over 2 times cosine of theta. So you need the product between this force and this distance to calculate the moment of this force with respect to this point. Right? Yeah, so this is the force and this is the distance. Similarly here, this mg is our force and L sine of theta is the distance, because now you have to look at this distance here. We can simplify a little bit our expression, and what we have is m L square theta double dot plus k L square over 2 times theta, because cosine theta is equal to 1, minus mgl sine theta is equal to theta, equal to 0. We can put these two quantities together, so we have m L square theta double dot plus k L square over 2 minus mg L times theta equal to 0. We actually have L square here, and L here, which means that we can get rid of this square here, and this L. So we can now write the equation in the standard form, which means that we have theta double dot plus KL over 2 minus mg divided by ml times theta equal to 0. So this is the equation of motion in standard form. So now that we look at this standard form, we know that we can determine the natural frequency. How do we determine the natural frequency? By looking at the term of by looking at the first order term, the theta here, because we have that basically the natural frequency would be the square root of KL over 2 minus mg divided by ml. Right? So let's try to write the natural frequency as square root of KL over 2 minus mg divided by ml. Any observation about this now? Do you notice anything? You can try to go back to other examples that we have seen so far, and you can look at how the natural frequency of other systems look like. Then you compare with this natural frequency, and maybe you can notice something. So they all take the form of square root of the elastic constant over the mass. There are always, this is for the simple harmonic oscillator, so we have like a spring and mass, or for example if we have more than one spring, we can find the K equivalent and then we divide the K equivalent over the mass. But there is something else that we can notice when we look at this expression of the natural frequency in comparison to what we have seen so far. Okay, can you please say again? I didn't hear. Yeah, it is a combination, because again this is not a simple harmonic oscillator, so we have the effect of the gravity, the effect of the spring, so of course both contributions are involved. But there is something else that we can notice. I was actually going back, looking at the notes. For example, this is another expression of the natural frequency that we found. Let's see. This is another expression. This is another expression of the natural frequency that we found. This is another expression of the natural frequency that we found. What else? This is another expression, G over L, of the natural frequency. Then we talk about logarithmic decrement. Let's see what else. This is another expression of the natural frequency that we found, where we have like the K equivalent with all these K's involved here. This was the amplitude. G over L, K over M. So the main difference between this expression of the natural frequency and the previous expressions of the natural frequency is that in the previous cases the natural frequency, sorry, it's a little bit loud, let me try to adjust. So in the previous expressions of the natural frequency, actually the term within the square root is always positive. Now if you go back and you look at all of them, you can see that it is always a combination of K, M, typically K and M, where again is a combination of K and M where this combination is always positive before this example here. But actually in this case, this combination is not always positive, because here we have a negative sign here, which means that this is positive only when KL over 2 minus mg is actually greater than 0. So there can be a situation in which this expression here, KL over 2 minus mg, is actually lower than 0, is negative. So in this case, when KL over 2 minus mg is negative, we talk about flatter instability. And what happened, instead of having the type of motion that we have seen so far, for example, when we talk about damped systems, when we have decrease of the amplitude, what happened in this case, again, when the term within the square root is negative, the type of motion that we see, the type of displacement, looks like this. So it goes, the amplitude increases instead of, staying the same when we have undamped system, or decrease when we have a damped system. So this is time and this is x. So we have to be careful. We always work with symbolic problems, or most of the time we work with symbolic problems. So it means that in a situation like this, again, we have to pay attention, because the system can be stable or unstable depending on the relation between K, L, M, and G. Makes sense? And this is an example where if this combination is negative, so KL over 2 minus mg is negative, the system becomes unstable and the amplitude increases instead of staying constant when we apply a certain initial displacement or initial velocity. Makes sense? Any question about this? If the mass is high enough, it depends with respect to KL over 2. I mean, again, we are starting from the assumption that we have like small displacements. So when we have an initial small displacement and then we have again that the combination of these quantities is negative, the deflection, instead of staying constant, it will increase. And then of course it can become so big that from a structural point of view is, first of all, not a small displacement anymore, and then we can be in a situation in which the force of the spring is not enough to hold the mass anymore, and then, you know, the whole system would collapse. Makes sense? Alright, we are 2 minutes over, so I think we are done for today. We are going to meet again Wednesday, and we will do a little bit of review before the exam that is next week. Alright? Have a good night. See you in a couple of days.